Hello everyone, today I will be presenting my Polygens project, which is called the analysis of a three-link robot arm simulation. So today I will be going over coordinate transformations and its kinematics, data storage and algorithms, how we collision check, some experiments, and finally the conclusion. All right. So first, let's go to a basic concept, which is coordinate transformations. So in this case, a robot arm cannot normally be represented, and instead it needs a new coordinate system. Coordinate systems are a foundational concept in robotics and engineering, and so given xy coordinates, a rotation of the regular plane by angle theta will result in a new coordinate system expressed, as you can see on the screen on the left with this diagram. And this concept, you can also express it in matrices form, as you can see here, or we can also express it in component form here. And this concept shall be useful for the remainder of this report. Okay, so another very important concept is kinematics. So forward kinematics provides the position and directional vector for robot arm end effector, and the end effector is basically this end point, which depends on x, y, and another angle. And you can see that the diagram as I showed below for the end effector, and it has the x and y coordinates. Inverse kinematics determines the configurations required to reach a goal, and in some cases, inverse kinematics will result in two solutions. So they result in multiple solutions. For example, if you only have a two-link robot arm, you can have two solutions. However, if you have three, you may have multiple. A Jacobian matrix is extremely useful in determining the linear angular motions of the end effector. So for the coordinates of the tip of this three-link, 1, 2, 3, three-link robot arm, we can express this in terms of theta 1, theta 2, and theta 3. And so this is a matrix representation, and I will be deriving that in the next slide. So the derivation is shown here. You can see that we take the partial derivative of the how the x value changes with respect to theta, theta 1, theta 2, and theta 3. So this can allow us to know how much the end effector position changes whenever we have either only theta 1 moving, or theta 2 moving, or theta 3, or a combination of some. And so when we derive all of these, this is just taking the derivative with respect to theta 1, theta 2, theta 3 of x and y. And so we have our new matrices form. Next, we'll go to a very key component of this entire scheme, which is algorithms. We use two algorithms. First, the inverse Jacobian algorithm, and second, the RRT algorithm. So algorithm 1, inverse Jacobian algorithm, is when we initialize Q. In robotics, we tend to use Q to initialize angles. Our current is equal to the forward kinematics, and the change in x is equal to our goal minus our current position. And while we're under a certain threshold of the goal, we keep on moving to the next point, and I'll show this visually in the next few slides. And so we end this while we are done. So we just end the while and then we return back to the angle. For RRT, it's a bit more complicated, but essentially we are doing a very similar fact. So while I, which is the number of iterations, is less than the overall number of iterations you want, pick a random beta value. Alpha and beta are essential in order to find path planning. And so this entire RRT algorithm will be explained in the next few slides. So first, we need to decide a way to store data. And so we decided to use dictionaries in Python because Python is the chosen language for this research project. RRT algorithm has a parent-child structure. So for example, you have a particular point, let's say here, you would have some value, let's say epsilon or any other variable you wish to have. You would extend by a small increment. And this can either be goal-oriented or it can be in a random direction, and that is what beta value does. So parent-child, so the parent will be the initial, so let's say the starting point, and then the point, the node extends in another direction. So it picks a random point, either random or or biased towards a specific direction, and then that is called the child. And so that is the value of the dictionary. The key of the dictionary is the parent. And so consistently, for every key, you have a value, and you consistently generate that. So algorithm chooses a point, creates another key corresponding to the selected point. It stores coordinates and the corresponding joint angles as the value, and it continues until the final sample is within the threshold of the goal. And the goal can, in most cases, cannot be reached perfectly because of various errors in measurements that happen. So we have a particular threshold for this. So how do we create new nodes? We have two values. We have alpha values and we have beta values. Alpha values determine the step size of each iteration. So that can increase our precision because our step sizes are very small, so we are more cautious. However, if we have a beta value, we determine the probability of there being a random configuration. So our node chooses a random point versus one that consistently moves towards the goal. So let's do some efficiency analysis. So if we have small alpha values, we increase our precision. But in some cases at the cost of time. However, if we have a lot of obstacles in our course, then that means small alpha values will be beneficial because if it's very large, we might not even have a solution in the first place. And a high value of beta, which is random, might cost time because we are not being biased towards this particular direction. So next idea is that in our case, so in measuring the distance required to move the 3-link robot arm from one configuration to another configuration, we do not consider the distance that the end effector has to travel. Instead, we determine, this is only for a 2-link, but it follows similar principles to a 3-link robot arm. Instead of just using the XY distance, we tend to use angles because they provide a better measurement. They provide us how to determine angle changes required to reach a particular configuration. And then the angles reveal the energy required to reach a goal configuration. So as you can see in this diagram, our 2 points are pretty close together in terms of XY. However, we notice that we have 2 possible options. So first, we have some angle here. Let's call this theta 2, and some angle here, theta 1. Note the large amount, the large angular displacement we have in terms of this blue link arm, and in terms of these 2 possibilities. That is quite large, which means large amounts of energy is required even if the XY distance is small. Next, let's go to a key factor in this entire RRT algorithm, which is collision check. And let's go over the geometry. So for collision check, for collision in general, I decided to use rectangles and squares and such quadrilaterals. And instead of having a separate XY coordinate for every single corner, we only chose to have one XY coordinate for one corner, as you can see, as it's circled, and the rest can be derived using angle measurements, which we have decided to use here too. And so feel free to look at the geometry. So if we have an XY point, we have our width, we have the height, and from that we can derive this corner, and the top corner too, which is shown here. And so there are some cases for collision check too. So for collision check, sometimes the rectangles may not be parallel to the X and Y plane. So this is a very simple case. However, instead of having X, Y, our rectangles may be slightly tilted over here. So then we need to create a new line like this. But that is in reference to the original. So we have to perform, as I stated in the 3rd slide about coordinate transformations, this is similar. We need to do a plane transformation in order to find values relative to the rectangles. And further, we have more collision check cases for this when the rectangle is within a large rectangle, but it's not inside this case, and another case. And these represent the A-min, B-min, A-max, B-min values that we have. Now going on to experiments, this is one key experiment we performed. Further experiments would be performed in the future. They're currently being performed as well. But for the sake of this presentation, this is the main experiment that I performed. So I used matplotlib to plot the steps taken, amount of steps taken, iterations, or the efficiency, if you want to call it that, relative to the alpha and beta value combination. So as you can see, we have alpha on this axis, beta on this axis, and on the y-axis, we have the efficiency, or this number of steps taken, so is here. In this case, we have efficiency without the obstacles, and you realize that efficiency is quite high. However, for 0.2 by 0.2 units square, realize that we have some red components, which means that our efficiency becomes very low, so it takes longer. Note that graph 1, which is this, maintains a lower cost, and at lower values of alpha and beta, efficiency is the lowest. So overall, in conclusion, so in this presentation, we evaluated the drawbacks and the benefits of used constants such as alpha and beta. This was done with obstacles and without obstacles. We found the advantages of using angular measurements, evaluated initial stages of finding combination of alpha and beta, and so thus we maximized efficiency. And this ultimately, especially these types of graphs, if they were done more frequently, they can contribute to finding novel algorithms to find optimal solutions of alpha beta combinations, and this can be beneficial somehow for path planning. And so this was all I had for today, and thank you for listening.